Some functions describing the physical world are dependent on more than one variable. For instance, according to the van der Waals equation of state for 1 mole of gas, the pressure of the gas depends on both its volume and temperature according to the universal gas constant times temperature divided by volume minus the van der Waals B constant minus the van der Waals A constant divided by the volume of the gas squared. When plotted for carbon dioxide, the van der Waals equation takes the form of a surface. For volumes between 1 and 5 liters and temperatures between 300 to 400 Kelvin, the allowed pressures of the gas in units of atmospheres fall on the plotted surface. The van der Waals pressure of 1 mole of gas is clearly dependent on two variables, volume and temperature. As another example, consider the function sine pi x times sine 2 pi y. A function like this appears in quantum mechanics. Its plot is a surface that ranges from -1 to +1 when x and y are allowed to vary from 0 to 1. Again, it is clear that the function depends on two coordinates at the same time. Many physical quantities depend on more than one variable, and so functions like this are unavoidable. Sometimes we need to find the derivative of functions that depend on more than one variable, such as f of x and y equal to x squared y plus y cubed x. But how do we do this? Evaluating the first derivative of multivariable functions involves taking the derivative with respect to each variable separately while treating all the other variables as constants. Because each of these derivatives is with respect to only one of the variables at a time, the derivatives are called partial derivatives. There will always be one partial derivative for each variable in a multivariable function. For our example function, there will be two, one with respect to x and one with respect to y. To distinguish derivatives of single variable functions from partial derivatives, we use different symbols. Instead of writing df dx, we write del f over del x, which is read as the partial of f with respect to x, meaning the partial derivative of f with respect to x. To emphasize that the other variables are held constant while evaluating this derivative, we sometimes write the partial derivative in parentheses with a subscript indicating the other variables, such as y, that were held constant. When an author wants to be even more succinct, she will sometimes write f sub x. For the other partial derivative, instead of writing df dy as we would for a single variable function, we write the partial derivative of f with respect to y, which again can be written with the variable x as a subscript to indicate that it is held constant while evaluating the partial derivative of f with respect to y. More compactly, you will sometimes see this written as f sub y. So let's evaluate the partial derivative of our example function with respect to x while holding the variable y constant. Holding y constant means to think of it as a constant, like 5 or 10, each time you encounter it. Using the sum rule, we evaluate the derivative of each term in the sum independently. The derivative of the first term with respect to x while holding y constant is 2xy, because the derivative of x squared is 2x, and because the variable y is treated as a constant that's just along for the ride. We add to this the derivative of the second term, which is y cubed, because the derivative of x to the first power is 1, and because y cubed is just a constant. The partial derivative of f with respect to y while holding x constant is found in a similar manner. The derivative of the first term with respect to y, treating x as a constant, is x squared, because the derivative of y to the first power is 1, and because x squared is treated as a constant. We add to this the derivative of the second term with respect to y, holding x constant, which is 3y squared x, because the derivative of y cubed is 3y squared, and because x is a constant. These are the partial derivatives of the function f. Of course, higher derivatives exist for multivariable functions as they do for functions of a single variable. Second derivatives can be evaluated by taking the partial derivative of the function twice with respect to x, each time treating the other variables as constant. This is read as the second partial derivative of f with respect to x. It can be written more compactly as f with the subscript xx. We can also take the second partial derivative of the function with respect to y, holding x constant, which can be written compactly as f sub yy. If the function were dependent on more than two variables, there would be more second partial derivatives. Let's evaluate these partial second derivatives of our example function, starting with the first partial derivative with respect to x and with respect to y that we have already evaluated. The second partial derivative with respect to x is the derivative of the first partial derivative with respect to x and is 2y, because the derivative of x is 1 and everything else is a constant. The second partial derivative of f with respect to y is the derivative of the first partial derivative with respect to y and is 6yx, because the derivative of y squared is 2y and x is a constant. Functions of multiple variables allow for another type of second derivative called a mixed partial second derivative. After evaluating the partial derivative of a function with respect to x, we could evaluate the partial derivative of that result with respect to y instead of x. This is written as the second partial of f with respect to first x and then y. Note that the derivative taken first is listed on the right in the denominator. Sometimes this is written as f sub xy, with the derivative taken first written first in the subscript. The same thing can be done for the partial derivative with respect to y. We could take the partial derivative of this result with respect to x. Using the same symbology as above, we have the second partial derivative of f with respect to y and then x. In compact notation, this is f sub yx with the derivative taken first, y, listed first in the subscript. Applying this to our example function, the partial derivative with respect to y of the partial derivative with respect to x, which we already have evaluated, is 2x plus 3y squared. While evaluating this derivative, x was treated as a constant because the derivative was being taken with respect to y. Likewise, we can evaluate the partial derivative with respect to x of the partial derivative of f with respect to y, which we already know, to obtain 2x plus 3y squared. In this evaluation, y has been treated as a constant because the derivative was with respect to x. The fact that these two mixed partial derivatives yield the same result is important, but that is best discussed in the context of a chemical topic where it is more relevant. Some other examples might help. Consider the function e to the negative 5x times sine of pi y. The partial derivative with respect to x is found by using both the product and chain rules while treating y as a constant. This partial derivative is negative 5 times e to the minus 5x times sine pi y. The derivative of this result with respect to x is the second partial derivative of f with respect to x and can be evaluated to be 25 e to the negative 5x times sine pi y. The partial derivative of the original function with respect to y is found with the product and chain rules, treating x as a constant, to be pi times e to the negative 5x times cosine pi y. The derivative of this with respect to y is the second partial of f with respect to y and can be evaluated to be negative pi squared e to the negative 5x times sine pi y. Remember that x was treated as a constant. Two mixed partial derivatives can be found, the second partial of f with respect to x first and then y, as well as the second partial of f with respect to y first and then x. These two mixed partial derivatives can be found by starting with the partial derivative with respect to x and evaluating its derivative with respect to y, or by starting with the partial derivative with respect to y and evaluating its derivative with respect to x. The results are the same and equal to negative 5 pi times e to the negative 5x times cosine pi y. A function of three variables is no more difficult. Let's consider sine pi x times sine 3 pi y times sine 4 pi z. The partial derivative with respect to x, treating both y and z as constants, is pi times cosine pi x times sine 3 pi y times sine 4 pi z. The constant pi in front comes from using the chain rule on sine pi x. The partial derivative with respect to y is 3 pi times sine pi x times cosine 3 pi y times sine 4 pi z. The 3 pi in front comes from applying the chain rule to sine 3 pi y. Finally, the partial derivative with respect to z is 4 pi times sine pi x times sine 3 pi y times cosine 4 pi z. Second partial derivatives and mixed partial derivatives can also be evaluated if you want or need them. That's the math, but what does a partial derivative mean geometrically and physically? As for functions of one variable, partial derivatives of multivariable functions can be interpreted as instantaneous rates of change and the slope of a tangent line. As a specific example, let's again consider the van der Waals equation for 1 mole of the gas carbon dioxide. The allowed pressures for each volume and temperature combination appears on the plotted surface. Let's say we want to know how the pressure of the gas changes when the volume changes at constant temperature. This is a verbal way of describing the partial derivative of pressure with respect to volume at constant temperature. To understand how this can be visualized on the plot, let's pick a constant temperature of 350 Kelvin and then draw a line along the van der Waals surface at a constant temperature of 350 Kelvin. So that we can better see what's going on, let's remove the surface below a temperature of 350 Kelvin. The edge of the surface at a constant temperature of 350 Kelvin forms a curve that shows pressure as a function of volume, and the partial derivative of pressure with respect to volume is the slope of the straight line tangent to the curve formed by that edge. The slope of this line, and therefore the partial derivative, changes at different volumes. The partial derivative of pressure with respect to volume at a constant temperature of 350 Kelvin is the instantaneous rate of change of the line formed by the intersection of the van der Waals surface and the plane that cuts the surface at a constant temperature of 350 Kelvin. All partial derivatives can be interpreted in a similar fashion. And that's partial derivatives.